Welcome back to Share Science, the weekly science brief for August 24th, 2026. I'm Curie.
And I'm Derek. Curie, I want to warn everybody up front. This week is a week of things being faster, bigger, and older than anyone had them pegged.
That's right. So imagine this, a star moving so fast that it could travel from New York to Los Angeles in just a sixth of a second. That's the kind of speed we're talking about today.
That's wild. I can't even wrap my head around that kind of speed. What's the story behind it?
It's all about S301, the fastest star ever found in our galaxy. This star is orbiting Sagittarius A star, the supermassive black hole at the center of the Milky Way. At its closest approach, it's moving at 25,000 kilometers per second, about 8% of the speed of light.
That's just insane. And it's orbiting a black hole, right? So, what makes this discovery so important?
Well, it's not just the speed that's impressive. S301 gets closer to the black hole than any other star we've tracked, which means it's in a unique position to help us measure something we've never been able to measure before: the spin of a supermassive black hole. Einstein's theory of general relativity predicts that a spinning black hole drags space-time around with it, an effect called frame dragging. But to detect that, you need a star that gets incredibly close, and S301 fits the bill.
So, if we can measure this, it's like unlocking a whole new level of understanding about black holes?
Exactly. Right now, we know the mass of Sagittarius A star, but its spin is still a mystery. If we can track S301's orbit over the next decade, we might finally be able to measure that spin directly. And that's huge, because spin is one of only 3 properties a black hole can have, the others being mass and charge.
And how did they even find this star? It's not like you can just look up and spot it with a telescope.
That's the amazing part. They used the Very Large Telescope Interferometer in Chile, which combines light from multiple telescopes to achieve incredible resolution. One of the researchers noticed a faint flicker in the data years ago and tracked it forward and backward until the orbit became clear. It's a perfect example of how patient, meticulous work can lead to groundbreaking discoveries.
Speaking of discoveries, let's shift from the stars to something a little closer to home, like the bottom of the ocean. What's this about Denisovan bones being dredged up by fishermen?
This is such a fascinating story. In the Penghu Channel between Taiwan and mainland China, fishermen have been pulling up fossilized bones from the seafloor. During the Ice Age, this area was dry land, and it's essentially a bone bed full of Ice Age animals, and apparently, humans. Among the fossils are 2 leg bones that are shedding new light on the Denisovans.
Remind me again who the Denisovans are? They're kind of like the mysterious cousins of the Neanderthals, right?
Exactly. They're an extinct branch of humans who lived across Asia. We first identified them through DNA from a finger bone found in a Siberian cave in 2010. But actual Denisovan fossils are incredibly rare, which makes these leg bones so exciting. They suggest that Denisovans were much taller and heavier than we previously thought.
How tall are we talking here?
Based on the femur, about 5 feet 11 inches and 183 pounds. The tibia suggests someone closer to 6 feet 3 inches and 200 pounds. For 45,000 years ago, that's massive. Bigger than Neanderthals and even larger than most Homo sapiens of the time.
But there's some debate about these findings, right? I think you mentioned this was a preprint?
That's right. The study hasn't been peer-reviewed yet, and some researchers are skeptical. They point out that estimating height from a single leg bone can be tricky, and the lack of context, these bones were dredged up, not excavated, makes it harder to draw firm conclusions. But even with those caveats, the fact that we're learning more about Denisovans from such a small number of fossils is incredible. Now, let's go back even further in time, 150 million years to be exact. We're talking about Archaeopteryx, the famous fossil that's been at the center of the dinosaur to bird story for over a century.
And the big question has always been, how did it get off the ground? Right? Did it glide from trees or did it take off from the ground?
Exactly. And a new study suggests it was a little of both. Archaeopteryx couldn't achieve flight with a single leap. Instead, it needed a sequence of hops, 2, maybe 3, before its wings could take over. The researchers built a biomechanical model of its hind limbs and found that a single jump wouldn't generate enough speed for flight. But multiple hops, combined with wing beats, would do the trick.
That's such a charming image. Hop, hop, flap. And this behavior isn't just a hypothesis, right? Didn't they find something similar in modern birds?
They did. Many modern birds, like crows and pigeons, often take off with a series of small hops before fully taking flight. It's a reminder that evolution doesn't always reinvent the wheel. Sometimes it just refines what's already there.
All right, let's talk about worms. Specifically, a worm with no mouth, no gut, and no anus. How does something like that even survive?
By farming bacteria. This worm, Elavius algarvensis, lives in Mediterranean sediment and has a symbiotic relationship with bacteria that live under its skin. These bacteria store carbon as a polymer called PHA, polyhydroxyalkanoates, which is essentially nature's original bioplastic.
Wait, the same kind of bioplastic we use for compostable cups?
The very same. And here's the groundbreaking part. Until now, we thought only microorganisms could break down PHAs. But this study found that animals across 9 different phyla can degrade them too. This means animals have been feeding on nature's bioplastic for hundreds of millions of years.
That's incredible. It also raises big questions about how we think about bioplastics in the environment.
Exactly. If animals can break down PHAs, it changes how we think about their role in ecosystems. And it could have implications for how we design and use bioplastics in the future. Finally, let's talk about sprinting. A new study found that 3 minutes of high-intensity sprints trigger a much larger molecular response in the blood than 90 minutes of moderate cycling.
That's a 100-fold difference, right? But you were careful to say this isn't a prescription.
Right. A bigger molecular response doesn't necessarily mean better health outcomes. The study shows that sprinting releases a wave of signaling molecules called exerkines, which help organs communicate during exercise. But it doesn't prove that sprinting is better than other forms of exercise. The best exercise is still the one you enjoy and can stick with.
So, what's the takeaway from all of this?
Look again. Whether it's a star orbiting a black hole, ancient bones, a fossil bird, a strange worm, or even your own workout routine, there's always more to discover if you're willing to ask new questions.
And sometimes the biggest discoveries come from things that were sitting right in front of us the whole time.
Exactly. Stay curious, everyone.